Hi and welcome to Unit 2 Topic 3 Video 1, and this is our topic on matrices, and in particular today and for the next 7 videos we're going to be looking at matrix arithmetic. So here's the learning goal, success criteria, some work related to the exercises we use, and here we go. So a matrix is an array of numbers, so it's a little bit like a vector. You would have done vectors in Unit 1, except it's two-dimensional, so we've got rows and columns. And it's how we store information. So think about an Excel spreadsheet, for example, and you might have an array of numbers in a table. Not so much like a frequency table or data collection, a little bit more like each number represents something specific and special. Matrices can be used for lots of different things, such as transformations of functions or shapes, which we're going to do a bit of later on in this topic. Storage of data and computation. Solving systems linear equations, we'll do a little bit of this later in the topic, and we'll do some of this in Unit 3. Dominance, and looking at dominance of teams in a competition. Population predictions, probability forecasting, and cryptography, and the list goes on. So there's plenty of reasons we might use a matrix, and we'll start using those later in this unit and in Unit 3. So here's a matrix. Now, a matrix might be named, as we've done here. We've called this one A. We're pretty boring with our names, but we can give it a name. A matrix will have an order. So this matrix is a 4 by 3 matrix because it has 4 rows and 3 columns. So it's an M by N matrix. There's our M rows and N columns. And we go M by N, and so in this case it's 4 by 3. Each value is called an element. So this is an element and it's in a cell. So down here you can see this element 7 is in cell 4-3. It's in the 4th row and the 3rd column. 9 is in cell 2-3. It's in the, this isn't 4-3, my apologies. This is 4-1. So it's in the 4th row and the 1st column. Whereas 9 here, that's in cell 2-3. It's in the 2nd row and the 3rd column. Every cell is filled, even 0 counts. You can't have empty cells. If there's nothing there, then we just assume it is 0. So that's kind of some of the definitions behind a matrix. Let's have a look at using a matrix to store data. So we're going to talk about food van sales for 4 members of the class. We've got Alzani, Chris, Adam and Dylan. And HD, Berg and wraps, so hot dogs, burgers and wraps, and these are the sales that these 4 students made in a food van. Now we can represent that as a matrix over here. And you can see there's nothing special here. We've just taken Alzani's numbers, 12, 2 and 3, and written 12, 2 and 3 into the top row, and that's our representation. Now we could also transcribe this matrix and make it a 3 by 4 matrix, where the names are on the top and the items they're selling are down the side. But that's a little bit less usual. Usually we're looking for some sort of dependence relationship, and so naturally you would go with the names first. What does the sum of each row represent? So the sum of each row, 12 plus 2 plus 3, is just the number of items that person sold. Whereas the sum of each column, 12 plus 1 plus 11 plus 8, is the number of hot dogs sold in total. So you can see that there's some information stored there that we can garner from that matrix. And this is how we communicate data to a computer. So we have information, we can send it to a computer in the matrix form, which is why this topic is so important. So let's have a look at an example. Consider the map shown. This might be just a map between 4 towns and connections between 4 towns. We're going to construct a matrix R that represents the number of direct connections between towns. So looking at how we can move from town to town, A, B, C and D. So let's have a look at matrix R. We've called it R. R is equal to, now I'm going to do a bit of a rough up here, we don't normally do this, but we could have A, B, C and D, and then A, B, C and D. And then our matrix will be a 4x4 matrix, and we start looking at connections, direct connections. A doesn't connect to A at all. B doesn't connect to B, C doesn't connect to C, and D doesn't connect to D. For that to happen, there would have to be this weird sort of loop like that, and we have none of those. A does connect to B, and this is going to be a nice reflective matrix. So if A connects to B, well, that means that B connects to A. A connects to C, and therefore C connects to A. A does not connect to D. B connects to C, no it doesn't. B connects to D once, and D connects to B once, and then C connects to D but twice. So I'm going to put a 2 here. So this is one way we can store information. This matrix now, which we've labelled but we might not have the labels on there, it represents how a set of towns are connected by direct routes. Okay, well that's the end of video 1. All the best.